Okay, hi everyone, welcome back. So first, a small announcement, we have homework, it's due in a week. I've just sent the actual homework by email to you, and you can also find it on the website. The homework is entirely about using the LINDO package for solving linear programming problems. We started talking about it a little bit in the end of last time, and today I want to talk a little bit more about it. It's basically very simple, but allows you to do much more complicated problems that we were able to do to solve before. So it's important to know how to operate it. Yeah.
Will we have exam questions based on LINDO?
Yes, so it is possible for you to have an exam question based on LINDO. You will not be allowed to use a computer on the exam, but the question could be of the type, here's the input to LINDO probe, here's the input to LINDO, here's the output that is generated, try to interpret such and such number, what does it mean? If you introduce such and such product, what will happen? Could be such questions. So we'll see what this program is capable of doing. So first of all, it's available for Windows. I'm not sure whether it's available for other platforms. If you don't have an access to a Windows computer, you can use LINDO in our computer lab in Wesley Green building on the 3rd floor. 300 anything. So let me open the LINDO program. So we will download from the website a free version of it. It's a trial version, and that's what is installed here. And it tells you that it can handle up to 150 constraints and 300 variables, and no more. Well, it's enough for our purposes. It's not enough for practical purposes. Practical problems do have many more constraints, typically into thousands or even 10,000s, and even the best programs, I mean, in general, can't really solve using simplest algorithm problems with kind of millions constraints, but there are other methods which sometimes can solve, so, but for us, let's stick to this 150 constraints. And first of all, it opens the window where you input the program, and the program will, the syntax is very natural. Say you want to maximize some function, so you write that you want to maximize, then you write down what function you want to maximize, say 8x plus 9y plus 2z. So that's our objective function. Then you want to say that it's subject to some constraints, so you write down subject to, then you write down the actual constraints. And I'll use some random numbers. 5y plus 6z, smaller or equal than 10, and 2x plus 9y plus 4z, smaller or equal than 3. So this will be our constraints, and finally, this program is not complete. You should add the word and. It will say that now you list all the constraints.
Does it have to be in standard form, or can you just?
Okay, so for now we'll. So our first example will be in standard form, but this program can handle many more kinds of problems. So first of all, when I write just these things, well, of course the program can figure out what are the variables, the letters. So first of all, let me solve it. So you click on solve. Sorry, you click on solve, then solve. It solves. It tells you that it did 2 iterations. It asks you whether you want to do sensitivity analysis. Now we'll answer no. It's some extra option. We'll close this dialog, and it outputs something. So it tells you the output starts here. What was before was output from the previous one. So here's the output. Number of iterations is 2. The linear programming optimum, first of all, it was found, which means the problem is bounded, and the objective function is 11.49, and the values for x, y, and z are such and such. So 1.41, 0.01, some very small number, and z happens to be 0. So it does solve the problem. Let me make some comments about the formulation of the problem itself. Side by side. Okay, so in this problem, it is implied that the problem is in standard form, which means all the variables which appear there, x, y, and z, are positive. So this is always implied. If you want to make some other assumptions, well, there is a way to make some other assumptions, right? Some variable is free or some variable is greater or equal to something. But by default, this program assumes that all the variables are positive. So in this solution, you'll get only positive solutions. Okay, so basically, I mean, to solve more or less any problem from that we found, that we considered in our course, you can just do this. Write it down, words maximize subject to and n. If it wasn't in standard form, convert it to standard form, and well, we'll get the solution. Even better, the solution does tell you some extra information. You can read out the dual prices, which are the optimal solution to the dual problem, what we call shadow prices of these constraints. It can tell you whether in each of these constraints you have slack or surplus, which means is this inequality actually pushed to its limit, or there is discrepancy between the left-hand side and right hand side. We'll talk about this extra information in a meaningful problem, but for now, let me just say that there are some, well, I want to explain a little bit about the syntax. So first of all, this thing can handle problems not in standard form. For example, if you want to minimize something, it has no problem doing this. So I want you to minimize, and of course, well, what is the minimum of this expression? Well, of course it's 0. If you want this to be the smallest number, well, it can be 0, but no less than this. So here is the solution. Also, if you want to save yourself typing time, you can shorten the words minimize and maximize to min and max. You can shorten the word subject to just st, which stands for subject to. And you can even shorten the less or equal sign to less than, like this. So this program interprets less sign or less or equal sign just the same way. Yeah.
So does it just assume that x, y, and z are greater than or equal to 0?
Yes. So by default, it assumes that x, y, and z are greater than 0. And of course, well, if you solve this new problem, which is a little bit shorter, you'll get the same solution. This is exactly the same problem. So when you start solving the homework problems, well, you can first, after you download, you can try to formulate some random problem and see whether you actually can write it down and whether you can make the software solve it. So play with it. Well, of course, we don't want to solve random problems. We want to solve some problems that we kind of understand what the solution means. And let me go back to our production problem that we discussed for maybe 3 weeks now, or maybe 2 weeks. I'll recall what it was. So our production problem. Was about this thing. You produce chairs, tables, and doors. You use resources which are wood, metal, and labor, and interact product. A chair uses up 1 unit of wood, 2 units of metal, 1 unit of labor, and you get profit of $15. A table, for the tables, corresponding numbers are 2, 1, 1, and 20. For doors, it is 5, 1, 1, 10. And the totals are 480, 360, and 260 units of labor. And the question is, what is the optimal production mix? Which means, how can you maximize the profit? So, instead of solving it using the simplest algorithm by hands, let's solve it using our LINDO program.
Just verify the numbers. We have to afford this? Or
Sorry?
I'm kind of like down on this.
So there is a free trial version on the website. You can go to the website. I'm not sure if I have the internet here. But let me try. Yes, I think I did. So to download it, you go to lindo.com. Click on downloads, and here you have download classic LINDO.
Yeah, I don't think that's valuable.
You just said earlier
It's for Windows, yes. So unfortunately, it seems to be only for Windows. Okay, so it is a zip file. You can unzip it and install it. And so, as I said, we have computer labs and Windows is installed there. Okay, so anyway, back to our problem. So we have this problem, we want to maximize the profit. Well, let's start writing down what we want to do. We want to maximize the profit, which is 15 times the number of chairs, plus 20 times the number of tables, plus 10 times the number of doors. If you want, you can use some meaningful names for the variables. It accepts any name up to 8 characters. So, I don't know, 15, let's say, chairs, plus 20 times tables, plus 10 times doors. So I will maximize this function, subject to the following constraints. The constraints will come from resources. The first resource is wood, so write down that I use in my production 1 times C plus 2 times T plus 5 times D units of wood, and I want this to be at most 480. Similarly for metal and labor, I use 2 times C plus 1 times T plus 1 times D units of metal, and I don't want this to be more than 360. I also use 1 unit of labor for each chair, 1 unit of labor for each table, and 1 unit of labor for each table, for each door. And I want to use at most 260 of those. And finally, This is the end of my constraint, so I type n. So this is my problem.
Should it be less than or equal to, or just less than? Or it doesn't
Yes.
matter?
So it should be less than or equal to. I will write just less than. This program interprets less than as less than or equal. So I mean, it's something about computers. They don't have less than or equal character, and it's shorter to write just smaller. And of course, I mean, in practice, it doesn't really matter. Well, I mean, if these numbers were constrained to the integers, then it actually doesn't matter whether it's smaller or smaller equal to n. But if they can be real numbers, then well, there is no practical difference between this and small equal to n. But anyway, this program actually interprets smaller sign as smaller equal. So, okay, so now let's try to solve this. Let's not do the sensitivity analysis yet. And we get this solution. So after 2 iterations, the program has found the optimal value. The optimal value is 5,000. The number of chairs, well, now I know it's number of chairs because the name of variable is C for chairs. And the number of chairs is 40, the number of tables is 220, the number of doors is 0, so we don't produce any doors. We have some information about resources. Unfortunately, well, this 0 is a slack of some resource, and it is the resource which appears in row number 2. Well, right now I can understand that this is row number 1, this is row number 2, so it's probably the one that corresponded to moon. It will become much less convenient to count the numbers in an actual long problem, so there is an option to do the following, kind of add some kind of, well, not comment, but rather a name to a constraint. So let's call this constraint the mood constraint. And the syntax is you type the name and then a bracket, closing bracket. The second one was about metal. And the last one was about labor. So I just gave names to the constraints. Let me solve this problem once again. Now the output is a little bit more readable. There is no slack in mood. It tells you the constraint is called mood, has no slack, which means this constraint about wood was pushed to its limit. The constraint about metal is not pushed to its limit. There is slack metal available, 60 units of slack of metal, and no slack in labor. So this tells you everything about the primal problem, the actual problem. It tells you what happened to the production mix, chairs, tables, doors, what happens to the resources, no slack in wood or labor, there is slack metal left. It tells you what is the objective function. By the way, it might be a good idea also to give a name to the objective function if you want the output to be more readable. So we want to maximize profit. So write maximize profit, which is this thing. It will make the output even more readable. So the profit is 5,000. Okay, so now we have the solution to the primal problem. So maybe first any questions about the primal problem, the syntax, or what we did.
Sorry, what do you write after metal? I can't see.
Oh,
Is it the bracket?
yes, so I write metal in the closing bracket.
Okay.
So I have no idea how to make it larger form. Yeah. Okay. So this is the problem, and I hope it's more readable now. Okay. What's good about this program, it outputs more information than it's being asked for. So it has an extra column for the dual problem. It actually solves the dual problem as well as the primal problem. And we have the reduced cost for the products, and it has the dual prices for the resources. So let's recall what this means. So first of all, this is some numbers. They're given to you. They are the solution of the dual problem. These are the decision variables for the dual problem by 1, by 2, by 3, corresponding to these three constraints. And these are the dual variables for the dual problem. The step variables for the dual problem. Let's recall what these numbers mean. Let's start with the dual prices. The dual prices of food is $5. $5 for 1 unit of food. Let's recall that what this means is if you can get 1 more unit of food, not 480 units of food, but 481 units of food, you will be able, using this optimal production mix, to derive a profit which is $5 larger. Well, before this we kind of proved it using some theorems, some computations, some summations, some I don't know what. Now we can at least check this in this particular problem quite easily. If you change the amount of food available from 480 to 481, and you solve the new problem, what is the new value of profit? Well, as expected, 5,000. So let's go back to the original problem. The dual price of metal, well, is 0. What it means? Well, metal is a slack resource. You have free use of the slack metal. If you get more metal, well, you don't know what to do with it. You will just add it to the slack. You will not be able to derive extra profits. So if you change this number to any number which is larger than this, I don't know, you get 1,000 more units of metal, you will still get the same profit, just more slack metal. So that was the meaning of the dual price of 0 for the metal. Well, for labor, kind of the same as for wood. We have some dual price for the labor. If you get 1 more unit of labor, you will be able to derive $10 more of profit. Now, the reduced costs. So these zeros, let me kind of leave them for now. This 25, what it means. This 25 is, well, it's kind of the shadow price of the constraint d greater or equal than 0. What it means is if somebody imposes on you a contract, you must produce at least $1. How much less profit will you be able to derive? And the answer is $25. In other words, the resources which you divert to production of $1 minus the amount of profit that you derive from a sale of $1 is 25. So it's the loss from producing $1. And of course, once again, you can check this quite explicitly. If you want to add a contract on producing at least $1, like this, then you should expect that the profit will decrease by 25. That's the meaning of this reduced cost. Let's see whether it actually happens. Well, yes, the profit did decrease by 25. and you do produce exactly one door. And now it's quite easy to understand why these reduced costs are zero. Because in this problem you do produce 40 chairs and 220 tables. So if somebody imposes on you a contract, well, now you should produce at least one chair, well, no problem, you already produce it. You incur no loss. So if the contract was instead of d greater than 1, that you want to produce at least one chair, well, of course there is no change in the profit. And no change in production mix, nothing. So this is the meaning of this reduced cost being zero.
What if the contract was such that you have to choose more chairs than the value is, you know? So if there's like 41 chairs.
Okay, yes. So of course if you increase this number, so this interpretation of reduced cost works only for small changes to the right hand sides. So if you change 480 by kind of 1, then you would expect the profit to increase by 5. If you increase it by 100, you don't really know. Same here. If you increase c greater than 0, if you increase it 0 to 1, well, the profit will decrease by the reduced cost. If you increase it by 100, well, you don't know what will happen. I mean, of course, you can find out by actually solving it, but not from this information. It's only about small changes in right hand sides. Okay, so let's remove this contract. Now we have information about the optimal production mix, about the reduced cost, about the shadow prices of resources. Now, sometimes it is interesting what will happen if, say, well, this data is not quite accurate. Say, the profit of 15 that you derive from the sale of chair is only an estimate. You don't really know what it is. You say, well, it should be about 15. But it might be interesting still what happens if this profit is, I don't know, 20 or 10. Will it change the optimal solution? If it will, how much will it change it? And there is, of course, the option of just going to the original problem and playing with the numbers. What will happen if you change it to 20? What will happen if you change it to 10? But we learn a method to analyze these questions a little bit better. But for now, we'll just see how this program can actually implement this method. How can it answer the question what will happen to the solution as you change the coefficients a little. So let me now solve this problem once again. But now I will perform sensitivity analysis. So now I get output which includes the solution of the problem and some extra table, and I'll try to explain what this table means. So first of all, it tells you what it is, ranges in which the basis is unchanged. Suppose you want to change this coefficient of c from, well, 15 to something else. Think about the kind of the geometric picture of what this problem is about. We have three variables, so the space of all possible solutions is three-dimensional space, like our physical space. Inside of it you have some constraints. One variable is positive, another variable is positive, third variable is positive, some combination of variables is smaller than something, another one is smaller than something. So we have some kind of polyhedron. Maybe so let me draw a two-dimensional kind of analog of this. But of course you shouldn't imagine figure which is hard to draw. I don't know how it looks like. Maybe something like this. I don't know how the actual region looks like, but you have some region of feasible solutions. Everything inside this region corresponds to some feasible solution. And you want to maximize some linear function. A linear function means, well, you fix some direction, and the function is, I don't know, 0 here, 1 here, 2 here, 3 here, 4 here, and so on. So it increases in this direction. And you want to find out where it is. Okay, I chose not really the good direction, but you change the feasible region a little bit. Like this. So you want to find out where this function is the largest, and well, from this picture you see that it is at this vertex. What happens if you change the coefficient in this linear function? Well, we'll change the direction just slightly. So as you change this direction just slightly, it is reasonable to expect that exactly the same solution will still be optimal. And the only question is, how much can you change these coefficients? And the answer is right here. So this table, the first one, tells you the following information. The current coefficient of the chairs in profit is 15. So you derive a profit of $15 from the sale of one share. If you increase it by $5, or if you decrease it by $5, the optimal solution will not change. This is something which you can actually check. If you So right now the optimal solution is produce 40 chairs and 220 tables at $0. If you change this coefficient to say 20 and see what happens, well, the solution is still the same. Of course, the actual profit did change. The linear function changed, but the constraints and the place where the actual optimal production mix did not change. So what this number tells you is that you can increase this coefficient that used to be 15 only by 5. If you increase it a little bit more, even by 6, like this, 21, then the solution will actually change. So let's check that this is actually so. Yes, so if you can derive profit of $21, you'll change the optimal solution, and in fact quite a bit. The best strategy is now to produce 100 chairs and 160 tables, compared to 40 chairs and 220 tables before. And that's kind of how sensitive our problem is to a change in these parameters, in profits that we derive from the sale of something. So you can go back to the original problem. It used to have coefficient 15. Okay. So similarly, you can decrease it by 5, which means if the profit is reduced all the way up to 10, still it will have the same production mix, but if it decreases to 9, you'll get a different one. Similarly for tables, now you derive a profit of 20. If you change it in the range from 20 minus 5, which is 15, to 20 plus 10, which is 30. So if the profit is between 15 and 30 for sale of one table, still this solution will be optimal. That's what this line tells you. This line tells you currently the profit from production of $1 is 10 if you increase it by 25 or up to by 25. So if it is anywhere, yes, and if you can, or if you decrease it by as much as you want, basically decrease it to 0, decrease it to minus 50. You actually incur a loss by production, by sale of a door. Still, the optimal solution will have no doors in production mix, which is reasonable. So if currently this profit is not enough to justify a production of one door, well, if you derive even less profit, and it doesn't matter how much less profit, you will still will not want to produce any doors. This number 25 actually should be already familiar. It has appeared in one other place in the solution. So let's think about what this number 25 means. It means if you increase the profit from sale of one door by 25, you still don't want to produce any doors. But if you increase it by a little bit more, by 26 or something like this, you might want to actually start producing doors.
Because the shallow price was $25, so that you lose $25 every time you produce them.
Exactly. So this thing, well, it's this 25. They actually must have coincided. It's not a coincidence that this is 25, the reduced cost of one door, and this allowable increasing coefficient. Of course, right now if you want to produce one door, you will lose $25 of profit. So how much should you increase the profit from the sale of one door for it to be actually a good idea to produce one door? Well, the answer is, if you increase it by 25, well, you're indifferent between producing doors or not producing doors. But if you increase it by 26, well, now you can do better by actually producing some doors. So this 25 and this 25 are actually the same thing. So maybe back to the question about what can be asked on an exam, could be a question like this. Here's the output of a LINDO program explained by the allowable increase in doors is the same as the shadow price, is the reduced cost of one door. Could be a reasonable question. Yes, you want to start somewhere?
So if you increase it exactly by 25,
Mhm.
then it seems like it doesn't do anything.
So if I increase it by 25, what will happen is you will be indifferent between switching resources from production of this optimal mix and the production of doors. Which means you should expect that there will be not just one solution, but several of them. Infinitely many.
And the computer just says don't do anything, basically.
Yes. So the computer will. Okay, so
Can we try
I.
that? See,
Hmm?
can we put 35 doors and see?
Yes. So I believe that the computer will find just one basic solution, it will not find all of them. So let's see, you have 35 here. Okay, so produced the same production mix and it still doesn't want to produce any doors. But if you increase this coefficient ever so slightly, you would expect some doors to be produced. So I actually don't know whether there is an option to find all solutions, not just one of them, all optimal solutions, not just one of them. No, I don't think. So basically, in this problem, there are, oh, maybe now it will show a different one. Okay, yes. So you see, this program, here's something interesting about this program. Once it solves one problem, it remembers the optimal solution, and then it starts from this optimal solution trying to find the optimal solution to another one. If you change the coefficients, it will not redo all the steps from scratch, it will start with the previous solution. Now, in this problem, for the reason that we discussed, we expect to have several optimal solutions. So we can try to force this program to find both of them. So let's say for this problem, we would expect our previous solution to be the only one, 40 to 120 and 0. And that's exactly what happens, 40 to 120 and 0. If you try to solve this problem, which, as we know, should have several solutions, well, it will find just the previous one. We didn't want a change. Now, if you solve this problem, well, we should expect the doors to be produced. And here are 20 doors which are produced. Now you go back to this problem with several solutions and solve it once again. And here's the optimal production mix now. It's not 40 to 120, it's this one. And the reason is, well, it basically,
Cancels out, right?
yes. So it basically, let me draw a picture for this. Suppose we have a domain which looks like this, and we have a function which increases in this direction. So, like this. And here it is reasonable that the level sets look like this, and the optimal solution is right here. Now imagine yourself rotating this arrow, changing the coefficient slightly. What will happen is, at some point, you'll get a problem with several solutions, where this function is actually attains the same values on this whole edge. This program will just output this one vertex. Now, if you rotate it even further, you'll get functions with such level set, and the optimal solution will switch to be this one. But now, if you rotate it back to this one, well, it will not want to make the jump yet. So if you rotate it back, it will output the solution right here. And that's exactly what we see here. Unfortunately, it doesn't tell you whether the solution that it found is unique or not, but you can kind of understand whether it is or not. I mean, how do you know whether the solution that you found in some problem is unique or not? Well, you look at the last row in the dictionary, the profit is 5,000 minus something times number of chairs, minus something times number of tables, minus something times number of doors, minus something times the slack in wood, minus something times the slack in whatever it is, metal, minus something times the slack in labor. So if you wanted if you wanted very much to understand whether the solution is unique or not, you would just figure out what these coefficients are. So what these coefficients? What are these coefficients? You can find them right here. So recall that the coefficients in the last row of the optimal dictionary are in fact the values of the optimal solution of the dual problem. So these things, let's say this one will come with a coefficient which is one decision variable in the dual problem which corresponds to this constraint, which means it is the dual price of wood. So this is 5. Similarly for metal it will be 0, for labor it will be 10, and vice versa, this will be the reduced costs. The values of these slack variables for the dual problem. And now you see that there are 4 zeros here, but only 3 of the variables are basic. I don't even know which ones are basic. I mean, I can figure out. I have 3 non-zero numbers here, so these variables must be basic. But they all they come with coefficient 0, but also this thing comes with coefficient 0, but it is non-basic. So in the optimal solution, you must have these two variables equal to 0, but here you might choose one of these variables as current parameter. Okay, but this is kind of, this is more subtle than what I wanted to convey here. So let me go back to the solution of the original problem. So, perform sensitivity analysis. So now we understand what is the meaning of this table. There is another one table that I also want to explain. It's about right-hand side changes. So these are the changes in these numbers, right-hand sides in the constraints. So what is the possible meaning of these numbers? So it tells you what happens if you increase the amount of, say, wood available, or decrease the amount of wood available, or increase the amount of metal available. Will the solution change or not? Well, maybe with metal, it is quite an easy question. You have slack metal available, so if you get more metal, the solution will not change. Or if you reduce the metal by an amount which is equal to the amount of slack metal available right now, it will still not change. So we go back to this table, and we see that the current right-hand side is 360 units of metal available. You can increase it as much as you want, the solution will not change, and you can decrease it by 60, and the solution will not change. So this 60 is in fact the same as this 60. The meaning of the other numbers is a little bit more subtle. So think about our picture. We have some feasible region and we want to change the constraints slightly. Of course, the actual optimal solution, if say this is the optimal solution, will be quite sensitive to changing the constraint which are pushed to their limits at this point. Say here, this constraint and this constraint, well, if you change those, this point will be moving. So if you change this constraint to, say, this constraint, the point will move from here to here. So is there a sense in which our solution did not change? Well, the solution did change. The actual production mix will change. What will not change is what variables will stay basic and what variables will stay non-basic. So in this solution, we pushed these two constraints to their limits. And if you change this constraint a little bit, just a little bit, you will still want to push this constraint and this constraint to their limits. But if you keep doing this, if you keep changing this constraint more and more, so if you push this line from here all the way up to here, the constraints that you want to push to their limits will change. So here it is still this and this, this and this, this and this still is okay, but this and this, or let's say this and this already, is not good, because these points are already outside of the feasible region. They don't satisfy this constraint. They are not to the right, to the left of this line. So you can increase the coefficient of this in the right hand side of this constraint only up to a point. Up to this point, the basic variables, which means just which variables are basic and which are non-basic, will not change. After this point, it will change. So let's go say to this line. Right now we have 480 units of food available. This line tells you if you increase the amount of food available by 40 or decrease it by 60, so basically if the amount of food is in the range from 420 to 520, then the basis will not change. What does it mean? What is the current basis? You can see, you can read it from here. Which variables are basic? The number of chairs, the number of tables, and metal. So, sorry, yes. Which are non-basic? The number of doors, the amount of food, the amount of labor. Slack wood and slack labor. So if you change this coefficient from 480, let's say, to 500, you would expect that these numbers will adjust somehow. But these numbers, 0, 0, 0, will not change. And we can see whether it is the case. So if you change this to 500, say, and solve the problem, well, the production mix did change. We have more slack metal, less chairs, the same number of tables for some reason. But the actual basis that you don't produce any doors, you use up all the wood and you use up all the labor, did not change. Of course, if you add too much wood, you will get some slack wood, and other constraints will be pushed to their limits. So if you have quite a lot of wood, in fact, if you increase this amount for 180 by any amount which is larger than 40, so if I say increase it by 50, 180 plus 50 is 530, you would expect the basis to change. And let's see whether it does. Okay, yes. Now you do have slack wood available, quite reasonable. You do have slack metal, and you don't produce any chairs. So now the amount of chairs, the variable of chairs became non-basic. It is 0. Okay, so let's go back to 480. No sensitivity analysis. Okay, and similarly, of course, for labor. If you increase the labor by the amount of labor by 20, you will not get any slack labor. If you increase by 50, you will get some slack labor left. Okay, so this is more or less what this program can do for you. It can do a little bit more. It can actually show you how the simplex algorithms perform step by step. If you ever wanted to check whether your calculations and homework were correct or whether you made some musical mistake, well, now you can try to play with this program. So here you can do just one pivot, let's say. You can say that you want a pivot with variable which is doors, and row which corresponds to metal, and you do some pivot. Or you can do the pivot which should be the pivot which is the actual pivot. We will not explore these options, so they are, you already know how to perform simplex algorithm. If you want, you can play with those. But for now, we'll just try to explore what this program allows you to do, in practice. What's good about this thing is you don't really care about the amount of computations that it performs. You just want to give it some problem and expect to get an answer. So now we can try to discuss problems which are actually complicated. Actually have lots of variables, lots of constraints, and see whether this LINDO can handle them. So before I go to the kind of complicated problem, maybe any questions about this LINDO? Okay, so let me formulate a new problem. The problem is as follows. So an investor has $90 on Monday. Every workday, which means Monday to Friday, you can use the following opportunity. Invest X dollars on that day. Reach it by half of X dollars on the following day. And get $2X at the beginning of the third day. The question is, how should he invest his money if he only has 1 week? And this opportunity is available only from Monday to Friday. So the question is, what investment schedule maximizes the return of the investor by Saturday. So this is the problem. The investor has $90, and on each day he can do the following. He can take X dollars and invest it somewhere, but then he has to follow up by investing half of that amount on the next day, and then in return on the third day, in the beginning of the third day, he will get $2X. So for instance, example schedule. I'm not saying it will be the optimal one, but one kind of obvious way to do this, well, to invest his money is like this. So I want to invest $90 in this opportunity. Well, I can't really invest $90 on the first day because I will not be able to follow up on the second day is $45. I just won't have the money. So maybe let me be smart and invest only $60 on the first day and follow up with $30 on the second day to get, well, twice the $60 on the third day. So invest $60 on Monday, make it by $30 on Tuesday. Now I used exactly $90 to get, according to this problem, I will get 2 times the amount that I invested on Monday, which means $120 on Wednesday. And actually, I get this $120 at the beginning of Wednesday, so now I can use this $120 to invest once again. Well, I do the same thing. I can't invest all of this $120, but I can try to be smart about it. I'll invest $80 right now and $40 the next day to collect, well, $240, sorry, twice the investment on the third day. So invest $80 on Wednesday, match by half of this amount on Thursday, get twice the investment, which means twice 80, $160 on Friday. And now I'm a little bit stuck. I have $160 on Friday, but I can't really do much with it. If I invest any amount, well, on Saturday I'll have to match it by half of this amount, and I'll get my profit only on Sunday. But what I want to maximize is the return by Saturday. So for some reason, Sunday is not working day, I can't collect my profit or something like this. So it seems that the best strategy is right now to do nothing and wait until Saturday. So wait until Saturday. So our profit is, well, we started with investing $90 and we got $160 by Saturday. The question is, can we do better? Is there a way to invest smarter? I mean, it is a little bit not nice to wait whole Friday and whole Saturday and do nothing about this. So maybe there is a way to invest smarter. Well, so this is a problem which, I mean, before we had a way to solve large problems, we probably would not want to try to solve this problem. It would be long. But now let's formulate this problem and just feed it to this LINDO package. The only problem for us is how to formulate this problem. We'll have to decide what are the variables, what are the constraints, and what we want to maximize. So maybe any ideas how to approach this? Maybe a good idea to start is to try to think, what are the parameters? Once I get the solution, what kind of numbers I want to be reported back to me. These will be the parameters.
Would it be possible to invest $70 on Monday, but then you only had 20 to invest on Tuesday, the leftover? Is that okay? Or does it have to be half what you
It
invested?
has to be
It
half.
has to be, so it's not.
So maybe let me add kind of assumption right here. Assumption. If the investment X dollars is not matched by $2 the next day, it is lost. So somehow you sign a contract that now you pay X, tomorrow you'll pay X by 2, and then you get 2X before you.
Could you say like have 5 variables? How much money you should invest in Monday? How much money you should invest in Tuesday?
Okay, yes. So it sounds very reasonable that if I want a schedule to be reported to me, investment schedule, I want at least to see the following numbers. How much should I invest on Monday? How much I should invest on Tuesday, Wednesday, Thursday, Friday? Okay, so let's try to formulate our problem, solve parameters. It will be as follows. It will be investments on Monday, Tuesday, Wednesday, Thursday, Friday, and we invest, let's say X1, X2, X3, X4, X5. So in this case, these indices 1 through 5 actually are somewhat meaningful. Thursday, Saturday, Thursday, Thursday, and Tuesday.
So the investments you make on Friday, do you get a return on that?
Okay, let's think about it. If I make an investment on Friday, I will have to mention by half of this investment on Saturday, and I'll get my profit on Sunday. So it means that actually it's not reasonable. I mean, it's not a good strategy to make an investment on Friday. So maybe I'll want X5 always to be 0. Or maybe I'll just not want to have any X5.
So, like, Saturday is our last day we can get money.
Yes.
Okay, so Thursday would be like our last investment that would actually give us. Okay. But
Yes.
X5 can actually never be 0 because it has to be half of X4.
No, this is the amount of money that you invest on that day. It's not the amount of money that you use to match the investment from previous day.
Oh, okay.
If you want to write down what is the amount of money that you match the investment from the previous day, well, on Monday you don't match anything, you don't have any investment made. On Tuesday you will have to match this amount, here you will have to match this amount, that amount, or 2. So on Saturday you'll get, I mean, you won't have to match anything because we already discussed that you don't make an investment on Friday. It's Saturday here. Okay. Now, a reasonable question to ask is, what are you trying to maximize? What is the objective function? Okay, yes. So it is the amount of money you get on Saturday. What is this amount of money? How does it depend on all these parameters?
2 times x1 is
Okay, let's think about it. So we started with objective function. Well, what happens to our money? We start with $90, then we invest x1, then we match it by x1 over 2, then we let me add the line for return. Because we not only spend money, we also get money back. So we don't get anything back on Monday, we don't get anything back on Tuesday. We do get 2x1 here, 2x2 here, 2x3 here. And also on Saturday we collect the investment for Thursday, 2x4. Okay, so I want to take 90, subtract x1, subtract x2 and x1 by 2, subtract x3, subtract x2 by 2, but add 2x1, subtract, and so on and so on. So you see that it is complicated, at least somewhat complicated. And also, we want some constraints. What will the constraints look like? I mean, what things will actually constrain us?
Don't you get actually worried about, consider the return on the previous day also. You can't just say that.
So,
Like for example, constraint for Wednesday, you would have to consider how much money you have at the end of Tuesday.
yes, exactly. So at the end of each day, we don't want to run out of money. That's the constraint. So we'll have from the 1, 2, 3, 4, 5 constraints for 5 days in which we spend money. In the end of this day, we don't want to run out of money. So we'll have to write down the amount of money on Monday, 90 minus x1, amount of money on Tuesday, 90 minus x1, minus x2 minus x1 by 2, amount of money on Wednesday, 90 minus x1 minus this, minus this, minus this, minus this, plus this. It looks, well, it's a good thing that we have only 5 days in work week, because otherwise we'll have to use just tremendous expressions. There is a trick of introducing kind of extra parameters which are not the numbers that you want to be reported back to you, but which still have some meaning for you. So let me introduce the following parameter. Amount of money at the beginning of the day. Let me just, for each day, write down, well, here I have 90. In general, I can express these amounts using these numbers. But let me for now write it like this. The amount on Tuesday, the amount of money on Wednesday, M4, M5, M6. So introduce those variables as kind of parameters. What's good about this? Well, first of all, I can write down the objective function quite easily using those. My objective function is just the amount of money I get on Saturday. Another thing which is good about those is that it is quite easy to actually express those in terms of the other parameters, to find some relations between these numbers and the parameters. For instance, what is the amount of money at the beginning of day 3? Well, it's the amount of money you got at the beginning of day 2 minus whatever you invested in day 2 plus the return you got at the beginning of day 3. What's good about this thing is you can just duplicate this thing over and over. The same thing exactly happens on Thursday and Friday. You don't have to think much. The amount of money on say, Thursday is the amount of money on Wednesday minus, just increase the indices by 1. Similarly for this amount. Well, we'll finish the formulation of this problem next time, and we'll see how the LINDO goes. Okay, see you next time.
It's a good one, eh?
Yeah, it's really thin. Did you get it from Best Buy?